Okay, so we talked at the end of SN2 reactions about the effects of nucleophilicity, leaving groupability, and about the solvent and how polar aprotic versus polar protic solvents would affect an SN2 reaction. Now let's do the same thing for SN1. So we have to remember the trends, first of all, for nucleophilicity and leaving groupability. Remember that leaving groupability is based on one thing: basicity inversely. So in terms of leaving groupability, what are the best leaving groups? The halogens, and of the halogens, which is the best leaving group of those? Iodide. When we look at nucleophilicity, just as a quick review, with nucleophilicity, when we're looking at a horizontal relationship, what is it based on? It's based on basicity, and that is a direct relationship. So if we're looking at nucleophilicity as we go from right to left, the nucleophilicity as well as the basicity increases. When we go down the periodic table, when we're looking at a vertical relationship, what does that depend on? That depends on polarizability, which is the size of the ion. And so as we go down the periodic table, the nucleophilicity increases, so that iodide was the best leaving group and also the best nucleophile. So, and we'll come back to solvent effects in a minute. So when we're looking at an SN1 reaction, we're looking at the reaction of these two steps. Remember that step one was the rate determining step, and that was the slow step in the reaction. So that's the step we're most interested in affecting, either through the nucleophile, through the leaving group, or through the solvent. And so let's talk about leaving groupability first, simply because we didn't talk about leaving groupability and how it reacted or how it affected an SN2 reaction. So the question is the leaving group part of the rate determining step? Is it part of the rate equation? And so if we think about an SN2 reaction, what was our rate equation? Our rate equation was that the rate equals K times the concentration of the alkyl halide times the nucleophile. Now I just flipped the nucleophile and alkyl halide here because the question is leaving groupability part of the rate equation? That's the leaving group, so yes it is. And how would having a better leaving group affect the rate? Well, if you think about in terms of the transition state, we have our nucleophile partially bonded to the carbon with the leaving group leaving. Here's our trigonal bipyramidal geometry of our transition state for the SN2 reaction. So a better leaving group, how would that affect the rate? Better leaving group is easier to leave, and so in this case, in an SN1 or an SN2 reaction, the better leaving group, the faster the rate. Okay. And it will turn out that for all of the reactions that we study, if you have a better leaving group, you have a faster rate. Now I said here SN1 that it would cause a faster rate. Well, let's come up here and take a look at this. So in this rate determining step then, the alkyl halide, we break the carbon halogen bond and make the carbocation. So is that leaving group then, is this leaving group part of the rate determining step? Yes. And we'll write the transition state here for this reaction in a minute because we didn't do that in the last lecture. So leaving groupability affects the rate of all reactions, SN1, SN2, and even E1 and E2 that we'll come to in later lectures. But better leaving group, faster reaction. Now, what about the nucleophilicity? Does the nucleophile affect the overall rate of the reaction? And in this case, the answer is no. In the case of SN1, the nucleophilicity does not affect the rate of the reaction. Why? Because the rate determining step for this reaction is step 1. Is the nucleophile part of the rate determining step? No. So once we form the carbocation, it doesn't matter whether this nucleophile is a good nucleophile or a poor nucleophile, it's going to react at the same rate. So nucleophilicity does play a role in SN2. Why? Because in an SN2 reaction, it's part of the transition state. It's a concerted one-step mechanism. It's part of that. But for SN1, it's not part of the rate determining step, and so it doesn't matter whether it's a good or poor nucleophile, the rate's going to be the same because the nucleophile is not part of the rate determining step. Now let's deal with solvent effects. For solvent effects, how would the solvent effects affect the step 1, the rate determining step? Well, in this rate determining step, I'm going to break the carbon-halogen bond and form a carbocation and the halide ion. Now, what's going to make this reaction go faster? If I can stabilize these ions. So what kind of solvent is going to stabilize these ions the best? Well, let's take a look at, for instance, a halide ion. Polar protic or polar aprotic, meaning polar hydroxylic or polar non-hydroxylic. Well, if you have a hydroxylic solvent, right, like an alcohol or water, you're going to have very good solvation because the delta positive hydrogen is going to solvate very well the negative leaving group, or the negative halide ion in this case. And the carbocation itself will be solvated better by having the delta minus oxygen of the alcohol. We'll get more into that in a few minutes. So when we have better solvation of the products, we're going to get a faster reaction. So in the case of the solvent, again, it's not a question of, whether the aprotic, right, the non-hydroxylic solvents, what effect they have. In this case, using a hydroxylic or a protic, or using a protic solvent, is going to cause the reaction to go faster because it's going to solvate these ions better, which is going to cause the rate determining step to occur faster. And we'll get a little bit into that, stabilizing the products, making the reaction go faster, in a few minutes when we talk about the Hammond's postulate. So that's the effect. Nucleophilicity does not have an effect in SN1. Leaving group ability always has an effect. And in the case of the solvents, the solvents that will make an SN1 reaction go faster are the hydroxylic protic polar solvents. Okay? So that's the effect of nucleophilicity, leaving group, and solvent effects on an SN1 reaction. Okay, so now let's talk a little bit about the relationship between thermodynamics and kinetics, and this idea of Hammond's postulate. So if I asked you, if I said, which reaction is going to occur faster? The reaction of tertiary butyl chloride or isobutyl chloride, which one is going to react faster in an SN1 reaction? Okay, and I'm going to leave the nucleophile out of this because the nucleophile, as we just saw, doesn't play an effect, doesn't have an effect on the overall rate of the reaction. So really what we're talking about is which of these two reactions will go faster? The formation of the tertiary carbocation or the formation of the secondary carbocation? And let me go ahead and stop the video here, and you can tell me which one would react faster. Now, this might be just a gut instinct. So I just want to know ahead of time, or I just want to know, what do you think is going to react faster? And your other option is that they both are going to react the same. Or the other option is, I don't honestly know. That's fine. So answer the question of which one's going to occur faster, tertiary, secondary, they're both going to occur at the same rate, or I don't know. So go ahead, I'll stop the tape, and then you can go ahead and put in your answer. Again, this could be just a guess or a gut feeling, and then we'll go from there. Okay, so what did you choose? Well, let's talk about, before I give you the answer, let's talk about how to approach this. We're going to have to connect thermodynamics and kinetics. Now, normally that's not done. My best example from general chemistry is that carbon that's in its solid form, meaning that carbon that's a diamond, being converted to carbon in a, carbon of diamond in a solid form, converting to carbon of solid in terms of becoming sort of a powdered graphite, that is a spontaneous process, meaning thermodynamically, the delta G for that process is negative, which means that the reaction is indeed spontaneous. Now, if you have a diamond, if you purchase a diamond, the old saying, a diamond is forever, is that really true? Well, just because the reaction is thermodynamically spontaneous doesn't tell us about the kinetics of the process. So we have to find a way to link thermodynamics, and in this case we're going to be looking at sort of a delta H value as opposed to delta G. We're going to be looking at delta H and spontaneity of the reaction, and also then the kinetics of the reaction. So what Hammond's postulate says is that if I plot my energy versus my reaction progress, which I'm going to do a lot in this course and the next course. First of all, if I have my reactants and my products. So if I have my reactants and my products, and I'm going through just a single, or I'm going through a single transition state, then we have to talk about the thermodynamics in terms of what is this reaction, endothermic, exothermic, or in this case, thermoneutral. This is thermoneutral, right? If the reactants end up with a higher energy than the products, as I go through my transition state down to my final products, that difference in energy, that delta H, is going to be what? Energy is given off. So products minus reactants is going to be negative, and that's going to be an exothermic reaction. On the other hand, if I reverse it and say the reactants and the products are a higher energy as we go this way, then the reactants have to absorb energy, and so that's a delta H with a positive. And so that is an endothermic reaction. So in terms of the traditional delta H values, we can determine delta H from the energies of the reactants and the products. And if energy is released, then it's exothermic. If energy needs to be gained to get to the products, it's endothermic. And what Hammond's postulate says is it relates the delta H to the activation energy. And this is the way that we use Hammond's postulate. Now, Hammond actually said something completely different, and there are ways to completely obliterate Hammond's postulate in terms of getting it totally wrong. But here's what happens. In Hammond's postulate, what he said was, what he actually said was that if you took a reactant, and let's say that you were going to be able to form two different products. So here's product one, and then here's product two. What Hammond found was, and I'll show you a video in a moment with a piece of paper that kind of illustrates this, that as the product gets more stable, the activation energy becomes less. So when the product becomes more stable, you get a lower activation energy than what you get if the product is higher in energy. And remember, in this case, and in all cases, the lower the energy, the more stable the product. Now, what Hammond talked about was the idea that when you have a more stable product, then what happens is that the position of the transition state actually then moves in one direction or the other, and the reactant and the transition state looks more like the reactant or more like the product. And so that's what Hammond talked about. But in this case, we're going to interpret this as the more stable the product, the lower the activation energy. Okay? And there is the Arrhenius equation, which you talked about in general chemistry. And in the Arrhenius equation said that the rate of the reaction was equal to some constant times e to the minus EA over RT, where R is the energy gas constant, T is the temperature, and activation energy is the EA. And it's a logarithmic function. So if I asked you the question, the larger the activation energy, the blank the reaction, in terms of kinetics, what would you say? The larger the activation energy, the slower the reaction. The smaller the activation energy, the faster the reaction. That comes from the Arrhenius equation, from the mathematics of the Arrhenius equation. The temperature has an effect on the rate of reaction, right? And so if I said, what happens to the rate if you heat the reaction, if you increase the temperature? If you increase the temperature, the reaction goes faster. If you lower the temperature, the reaction goes slower. So the Arrhenius equation gives us the relationship between activation energy, temperature, and rate. Hammond's postulate basically said that if you make the product more stable, it'll have a lower activation energy and it will be formed faster. Okay? That's what Hammond's postulate, the way we interpret Hammond's postulate in beginning organic chemistry. So how does that help with this analysis? Well, if you're going to write out an energy coordinate diagram, and we're going to start with the alkyl halide, which is going to have roughly the same energy regardless of whether it's primary or secondary or tertiary. Let's say that I'm going to form here a secondary carbocation, and then I'm going to form a tertiary carbocation. The tertiary carbocation has the lower energy, and therefore what? Therefore, it should have a lower activation energy. Lower activation energy means, by Arrhenius equation, faster rate. So remember, this is the rate determining step for an SN1 reaction. So we would expect that a tertiary halide is going to undergo an SN1 reaction faster than a secondary halide. Why? Because it's forming a more stable carbocation. And now these aren't products, these are intermediates, right? But this is the rate determining step. So forming the more stable carbocation is going to occur faster than forming the secondary less stable carbocation. So that's how we interpret Hammond's postulate within organic chemistry and within SN1 reactions. So that's the relationship between thermodynamics and kinetics. So that when I'm establishing the rate of the SN1 reaction that's going to occur fastest is with the tertiary, then the secondary, and then finally the primary doesn't react in SN1 because it doesn't form a stable carbocation. So that's our kinetics and thermodynamics relationship through the Hammond's postulate, or through an interpretation of the Hammond's postulate. Okay? So let's talk about the sort of mechanism for an SN1 reaction, and now let's write a complete mechanism with transition states and the whole 9 yards. And now let's do this SN1 reaction. Actually, let's go back and let's do an SN1 reaction for what we did in the last lecture. So let's say I take tertiary butyl bromide and I react it with hydroxide. So let's write a complete mechanism for this, and let's include the transition states. So in the first step of the mechanism, I'm going to break the carbon-bromine bond and give that pair of electrons to the bromine. Okay, so that means I'm going to have my tertiary butyl group. I'm breaking the carbon-bromine bond, so that means in the transition state it's going to have a dotted line. And we'll come back to that transition state here in a moment. But what am I forming? I'm forming a tertiary carbocation and the Br minus. So basically what I can do is I can say, well, the transition state would be the average of CBr bond, no CBr bond, and partial CBr bond. How about the charges? Because the transition state is always the average of the bonds and charges. So carbon over here is 0, carbon here plus 1, carbon here delta plus. Bromine 0, bromine minus 1, average bromine delta minus. So what's happening in the transition state? I'm breaking the carbon-bromine bond, and where's the pair of electrons going? To the bromine. That's why it's delta minus. It's going away from the carbon. That's why it's delta plus. Okay, so that's the first step in the mechanism. Then I take my carbocation, and I'm now going to react it with my hydroxide ion. My hydroxide ion is going to come in and add to that carbon. That's what this arrow tells you. The arrow tells you that I'm taking the pair of electrons and I'm giving it to this carbon, or actually I'm sharing it with that carbon. So what would be the final product? The final product is then going to have the OH attached to the carbon. What's the transition state going to look like? The transition state, what bond am I forming? I'm forming the carbon-oxygen bond. How about my charges? Positive to 0. The carbon's delta positive. The oxygen is going from -1 to 0. It's going to be delta minus. So that's the transition state for that SN1 reaction. And so this would be step 1, the rate determining step, and then this would be step number 2, which is the fast step to get the final product. So this is a complete mechanism for an SN1 reaction with a negatively charged nucleophile with, in this case, a tertiary halide. Okay, so now let's change the conditions a little bit. Now let's use water. And water has an oxygen with no negative charge, but lone pairs. So it is still a nucleophile. However, when we classify nucleophiles, we talked about the relationship on the periodic table. What I didn't talk about then, which is relevant now, is charge. So I consider all strong nucleophiles to have a negative charge. Okay, and then you can look at the differences between the strong nucleophiles by looking at the periodic table. I consider a weak nucleophile to be a neutral, but it still has lone pairs. And so the two examples of weak nucleophiles are HOH, which is water, and ROH, which is an alcohol. So we classify nucleophiles as either strong or weak. Strong, in my world, it has a negative charge. Weak is neutral. And there are two neutral, water and alcohol. So when we react a neutral nucleophile with a tertiary halide, oftentimes the water is the solvent. And so this reaction is going to be called a solvolysis reaction, literally cleavage of the solvent. So how does the mechanism vary in the reaction of a neutral nucleophile with that of a negative charged nucleophile? Well, the simple answer is it adds one more step. So let's go ahead and write out and look at the mechanism, and then we'll go ahead and write it out with the transition states. So the first step is the same regardless of the type of nucleophile that you have. I'm going to break the carbon-bromine bond and form the carbocation. So what I'm going to do here is I'm going to write my transition state that I just wrote in the last reaction. So the transition state is going to have a delta positively charged carbon, a delta negatively charged bromine. So that will give me the opportunity to form then the carbocation. But now the water molecule, the entire water molecule as the nucleophile has to add to the carbocation. And we can't break up the water, right? We just can't say spontaneously, well, I'm going to break up that water into an H plus and an OH minus, right? I can't do that. Then if you're like, well, wait, we did something like that in general chemistry. Actually, you did. But remember that this is called the Ka. This is the autoionization equilibrium of water. And how big is this equilibrium constant? It is 10 to the minus 14th. How much hydroxide is present in pure water? Not very much. So in organic, we're going to treat this as the entire nucleophile. Do not break up the water. Make it a neutral nucleophile. And so what happens? The water's oxygen takes a lone pair of electrons and it donates it to the carbon, to the carbocation to form the bond. So this pair of electrons right here was this lone pair. And the oxygen is left with one lone pair because it used up one to form this bond. Now, here's the critical part about when you're starting to write mechanisms and you're starting to write steps. You cannot create or lose atoms, and you cannot create or lose charge. So when I took this neutral molecule, what did I make? A plus one, minus one. So I didn't lose any charge. When I'm reacting a plus one species with a neutral species, I get a plus one species. But where's the formal charge? Where's the positive one formal charge? It's on this oxygen, right? Because now this oxygen owns 1, 2, 3, 4, 5 electrons. It came with 6, it now owns 5, so it gets a positive 1 charge. You might say, well, where did the 6th electron go? It went formally to the carbon, because now if the carbon-oxygen split, they each get an electron, so the oxygen's lost ownership of one of its electrons. Okay, so always add the entire neutral nucleophile to the carbocation. So that would be step 2. What would the transition state for this look like? The transition state would have a partial bond between the carbon and the water. That's the bond that's forming over here. And charges would be carbon plus, carbon 0, carbon gets a delta plus, oxygen is 0, plus 1, the oxygen gets a delta plus charge. So this is the transition state. And it looks kind of strange, right? You say, well, I've got 2 delta positive charge next to it. That's not very stable. Well, this is a transition state. It's not going to be very stable anyway. But what's happening? I'm forming the carbon-oxygen bond, and the positive charge is being transferred from the carbon to the oxygen. And that's what the transition state tells me. Okay? So now, final step. That oxygen is extremely unhappy as a positive, so what's it want to do? It wants to lose H plus to form the final product. Now, how does that happen? That happens like this. Water is the solvent. And so what's going to happen is the water molecule as the solvent is going to come in and sort of grab that hydrogen. But I'm going to modify that statement in a minute. Then this pair of electrons in the OH bond, the OH bond is going to break and the pair of electrons is going to go back to the oxygen. So in the end, what will happen is I will end up with the hydrogen attached to this oxygen forming an H3O plus species, and then the oxygen in the product will go back to being neutral. So I will get the hydronium ion and the final product. Now, this is the way textbooks write it, and this is the full sort of mechanism way of doing this. But I don't want to leave you with a false impression here. The false impression would be that the water comes in here and rips the hydrogen off. No, the water is not that strong a base. Instead, think of it this way. The H plus, the oxygen-hydrogen bond is breaking, and the H plus is just kind of falling into the arms of the oxygen. The oxygen is not as aggressive on the water as it just kind of picks up the H plus as it's lost. Okay? So it's not that this is a strong base, it's picking up the H plus. And so what would the transition state for this be? The transition state for this reaction would be, what bond am I breaking? I'm breaking the OH bond. What bond am I making? I'm making the hydrogen to water bond. So I get 2 partial bonds here. In terms of charges, oxygen of the final product goes from +1 to 0. It gets a delta plus. And the oxygen of the water is going from 0 to +1, so it gets a delta plus charge as well. So this would be the full transition state for that reaction. Okay, so what we just did was we just wrote the complete mechanism for a solvolysis reaction of a neutral nucleophile water with a tertiary alkyl halide. And that is going to be an SN1 mechanism. Now, I'm going to just make a statement that I will make later on. And that is that whenever you react a neutral nucleophile with an alkyl halide, the only way the neutral nucleophile can add is if you go through a carbocation intermediate, which means the reaction must be an SN1 mechanism. If you cannot form a carbocation, then the reaction will not go. So neutral nucleophiles can only react with alkyl halides that can form stable carbocations, which means neutral nucleophiles can only react with secondary and tertiary alkyl halides, since they're the only ones that can form a stable carbocation. Okay, and we'll come back to that because we'll build a chart here in the future that'll allow us to predict whether we have an SN1 or SN2 reaction. Now, in terms of the energy coordinate diagram, here's the energy coordinate diagram for that reaction. The first is the formation of the carbocation, and then the water adding to form the formation of the second intermediate, which is the oxonium ion, which is then, you lose the H plus here, the water comes in and grabs the H plus, so that the final product then is this alcohol. Okay, so in an SN1 reaction with a neutral nucleophile, we have 1, 2, 3 transition states and 2 intermediates. Whereas before, we had, with a negatively charged nucleophile, we just had 2 transition states and a single intermediate. So that's the difference between a neutral nucleophile reacting in a solvolysis reaction and a negatively charged nucleophile reacting in the case of a SN1 that is not solvolysis. Okay. So then, in terms of kinetics, what happens? Again, the first step is the slow step. That's the rate determining step. So, does nucleophile strength happen? Or does nucleophile strength affect the rate of the reaction? It doesn't, right? So you're going to get the same rate whether you use a strong nucleophile in an SN1 or you use a weak nucleophile. Because in the rate determining step the nucleophile's not here, they both occur at the same rate. So nucleophile strength does not affect the overall rate of the reaction for SN1. Okay. Okay, so here is another example of a reaction that you could do via SN1. If you're an overly ambitious go-getter student, what you could do at this point is you could stop the video and you could write out the mechanism of this and then come back and see if you're correct. All right, so if you're not an overly ambitious go-getter student and you need another example, here's another example. You might be overly ambitious, but you just need another example. So let's write the mechanism for this reaction. So first step, break the carbon-bromine bond. Transition state would be partial carbon-bromine bond. Then to form the tertiary carbocation and the Br minus. That's the bond we're breaking, so that gets the dotted line. That's the partial bond. The carbon is going from 0 to +1, so it gets a delta positive charge. The bromine's going from 0 to -1. It gets a delta negative charge. And then in the second step, and let me show you how we would write the second step. So we don't have to start all over again with the mechanism. I could say, I'm going to take this pair of electrons and I'm going to react it. I'm going to donate it to that carbon. So what I could do is I could continue my mechanism on. And now in this case, what's going to happen? I'm going to have a partial bond from the carbon to the CH3OH molecule, which now, there's no one, and I should make this point. Notice that in the transition states, there's never any lone pairs. So this would be the transition state of that reaction as the oxygen's donating the lone pairs to the carbon. In the end, what do I end up with? I end up with the oxygen attached to the carbon with one lone pair and a positive charge. So what is the partial bond that's being formed between carbon and oxygen? Charge carbon +1, 0, carbon delta plus charge. Oxygen 0 to +1, oxygen gets a delta plus charge. So this is the transition state for the second step. And now in the third step, what happens? In the third step, my solvent, the methanol molecule, is going to come in and grab that hydrogen, and then this pair of electrons is going to, the OH bond is going to break and go to the oxygen. So if that's the case, I'm going to do my final step here, and my final step down here is going to have the O attached to the CH3, and that pair of electrons, the oxygen, will now have 2 lone pairs, and then the CH3O will now have 2 hydrogens bonded to it with a lone pair, and it will now have a positive charge. And so that's the final product. So in terms of the transition state, what do I have? I'm breaking the oxygen-hydrogen bond, and I am forming an oxygen to a CH3OH, and then up here's my CH3. And so oxygen then is going in this transition state. The oxygen is going from +1 to 0, so it gets a delta plus. This oxygen is going from 0 to +1, it gets a delta plus. And so therefore, that's the transition state for that final step. So this would be a complete solvolysis SN1 mechanism. Okay? So that's how we would write that complete mechanism. So in terms of SN1 reactivities, we'll deal with benzylic and allylic halides in the future. But tertiaries react the fastest, then secondaries, and primaries do not react in SN1. Why? Because you can't form a primary carbocation. Why is tertiary the fastest? Because the tertiary carbocation is more stable than secondary. Okay. So that's the big red circle through it for primary halides. They do not react in SN1 because they don't form stable carbocations. But that's okay, right? Primaries react the fastest in SN2. So SN1 and SN2 are complementary mechanisms. Tertiary doesn't go SN2, but it can go SN1. Primaries, SN2, but not SN1. Again, the real problem are the secondaries. Where should they go? And so we'll clarify that a little bit more. Okay? Okay, so that's the end of this lecture video over solvolysis and also Hammond's postulate that tells us why tertiary halides react faster than secondaries in an SN1 mechanism. Okay, so in the next video we will continue to talk about SN1, and then we will finish up and move into the next mechanism.